Welcome to TechPulse, where innovation meets exploration. In this dynamic channel, we're diving headfirst into the ever-evolving world of technology, bringing you a pulse on the latest trends, breakthroughs, and discoveries that shape our digital landscape. From cutting-edge gadgets and software wonders to in-depth analyses of industry giants and up-and-coming startups, TechPulse is your go-to source for all things tech. Join us as we unravel the complexities of the digital realm, presenting complex concepts in a digestible and engaging manner. Whether you're a tech enthusiast, a curious learner, or someone simply looking to stay informed in this fast-paced digital age, TechPulse is here to be your guide. Join us on this exciting journey as we decode the future, one pixel at a time. Subscribe, hit that notification bell, and get ready to embark on an exhilarating adventure through the world of technology. Welcome to TechPulse, where every video is a heartbeat of technological wonder. Sound is a fascinating phenomenon that enriches our world with its vibrational beauty. It is a form of energy that travels in the form of waves through various mediums, typically air but also liquids and solids. Sound waves are a crucial part of our daily lives, shaping our experiences, communication, and understanding of the environment around us. At the heart of sound is the concept of a wave. A wave is a disturbance that propagates through a medium, carrying energy without displacing the medium itself. In the case of sound, the medium is usually air. When an object vibrates or moves back and forth rapidly, it creates a disturbance in the surrounding air molecules. These disturbances, in turn, create a series of compressions, regions of high pressure, and rarefactions, regions of low pressure, that travel outward in all directions as a sound wave. The characteristics of sound waves are defined by several properties. Frequency. This refers to the number of vibrations or cycles the sound wave completes in a unit of time. It is measured in Hz, Hz. Higher frequency waves are perceived as higher-pitched sounds, while lower frequency waves are associated with lower-pitched sounds. Amplitude. Amplitude measures the maximum displacement of air molecules from their resting position as the wave passes through. Greater amplitude corresponds to a louder sound, while smaller amplitude results in a quieter sound. Wavelength. Wavelength is the distance between two consecutive points in a sound wave that are in phase, such as two crests or two troughs. It is inversely proportional to the frequency. Higher frequency waves have shorter wavelengths. Speed. The speed of sound varies depending on the medium through which it travels. In dry air at room temperature, sound travels at approximately 343 meters per second, 1235 kilometers per hour. Phase. The phase of a sound wave refers to its position within its cycle at a particular point in time. It is crucial for understanding interference patterns when multiple sound waves interact. Humans and many animals have evolved the ability to perceive and interpret sound waves through specialized sensory organs, such as ears. When sound waves enter our ears, they cause our eardrums to vibrate. These vibrations are then transmitted through a series of tiny bones in the middle ear and transformed into electrical signals that the brain interprets as sound. The study of sound and waves extends far beyond everyday experience. It finds applications in fields ranging from music and entertainment to medicine, engineering, and communication. For example, ultrasound uses high-frequency sound waves to visualize the inside of the body and diagnose medical conditions without invasive procedures. In engineering, an understanding of sound waves is crucial for designing acoustic environments that minimize unwanted noise or enhance desired sounds. Propagation of sound waves. Sound waves propagate in a manner similar to ripples on the surface of a pond. As they move through a medium, they transfer energy without transporting matter over long distances. However, it's important to note that sound waves cannot travel through a vacuum, as they require a medium to propagate. This is why sound doesn't travel in space where there's no air or other matter to carry the waves. Types of sound waves. There are two primary types of sound waves: longitudinal waves and transverse waves. Longitudinal waves. In a longitudinal sound wave, the particles of the medium vibrate parallel to the direction of the wave's motion. This is commonly seen in compressions and rarefactions as the wave passes through air. A simple example is the compression and rarefaction of air molecules when a tuning fork is struck. Transverse waves. While less common in the context of sound, transverse waves occur when the particles of the medium move perpendicular to the direction of the wave. This is more often seen in waves like light waves. Sound propagation speed. The speed of sound varies depending on the properties of the medium through which it travels. In general, sound travels faster through denser mediums and slower through less dense ones. For example, sound travels much faster through water than it does through air, and even faster through solids like steel. This property is used in various practical applications, such as underwater communication and earthquake detection. Doppler effect. The Doppler effect is a phenomenon observed when there is relative motion between a sound source and an observer. It causes a change in the frequency and pitch of the sound heard by the observer. As the source approaches, the sound waves are compressed, resulting in a higher frequency, higher pitch. As the source moves away, the sound waves are stretched, leading to a lower frequency, lower pitch. This effect is responsible for the change in pitch of a siren as it passes by. Harmonics and resonance. When an object vibrates, it often produces a fundamental frequency along with a series of higher frequency overtones or harmonics. These harmonics give different musical instruments their distinct sounds. Resonance occurs when an object is exposed to a frequency that matches its natural frequency of vibration, causing it to vibrate with greater amplitude. This phenomenon is exploited in musical instruments like guitars and violins, where the resonance of the body amplifies the sound produced by the strings. Ultrasonics and infrasonics. Beyond the range of human hearing, there are ultrasonic, above the audible range, and infrasonic, below the audible range, sound waves. Ultrasonic waves find applications in medical imaging, cleaning processes, and even in pest control. Infrasonic waves can be produced by natural phenomena like earthquakes and can have physiological and psychological effects on humans. In conclusion, sound waves are a fundamental aspect of our world that have been studied and harnessed for centuries. Their properties and behaviors have led to advancements in science, technology, and various industries, enriching our lives in ways we might not always realize. From the symphony of music to the practicality of communication and medical imaging, sound waves continue to shape and define our experiences.